All right, ready?
Yep, you're recording.
All right, cool. All right. So when we did the one-link robot, you were given a robot or an arm of certain length and certain angular position theta. This theta didn't change with time. So if you wanted to analyze the same link at another angular position, you would have to physically go and move to another position in time. Now imagine if I were to connect a motor to this link. It's going to go round and round. Right? And at every position, there's going to be a different value of L cosine theta and L sine theta because this theta is no longer a constant. So theta is now a function of time. Okay, and that's the focus of this chapter. So if you have a one-link robot that's rotating, now before x was L cosine theta and y was L sine theta. If theta is constant, that works fine. Now theta is not a constant, so I'm going to write it this way. Theta is a function of time, so x is going to be equal to L cosine theta, and theta is now a function of time, and I define it as a new variable, omega times t. And y, similarly, will be L sine theta of t, or L sine omega of t. Okay? This omega here is it's typically the angular velocity, but your book calls it angular frequency, so I'm going to use the same language. Angular frequency in radians per second. Okay. So in this expression, theta of t is nothing but omega times t. Omega is in radians per second. Time is in seconds. The 2 seconds will cancel out and you'll get theta of t in radians. Okay, and we define another quantity called capital T. Okay, which is defined as the period. Okay, so for example, if this arm went around a full circle so this is 360 degrees, right? So if it went around a full circle, theta would be 2 pi radians. And let's say it did this in 1 second. So the angular frequency would be 2 pi radians per second.
T equals like the period of the circuit, or the period of the cycle?
T is the period, yeah. So let me define. Okay, so if it completes 2 pi radians in, let me plot this first. Okay, so let me pull MATLAB to show you how to do this. Do you mind lowering the light, please? Thank you. Maybe both. Let's see how it works. Is there a button there? Oh, yep, it's coming on. So while we're waiting for that, okay, here it is. Okay, so all these codes are available for you. You could go to Blackboard and download these codes, and this will help you a lot in your homework. So for the very first problem, let's see what I do here. So I create theta goes from 0 to 6 pi. So 2 pi is one full rotation. So 6 pi is 3 times that. And I do it in 2,160 steps. Okay, and I say define length to be 1. And I say x equals 1 cosine theta and y equals 1 sine theta. So for the first plot here, theta is not a function of time. And this is what it looks like. So I'm plotting x cosine theta and x sine theta, or L cosine theta and L sine theta, I'm sorry, as a function of theta, and this is what the plot looks like. So notice that the x-axis is only theta, it's not a function of time. So what I do next is I'm plotting both of these as a function of time. All right, so x equals L cosine omega t, y equals L sine omega t, where omega is 2 pi over t. That is your period. So you want to know how the period is related to your frequency. So omega is the number of, so this is angular frequency in radians per second. This is how many radians it travels in how many seconds. That's what this symbol means, omega equals 2 pi over t. And that's exactly what I'm plotting here. I'm plotting x, which is L cosine theta, where theta is omega t. So L cosine omega t is the blue line, and L sine omega t is the red line. Okay? And this is a function of time. Okay? What's the difference between figure 2 and figure 3 here? They are both position versus time. This is for 6 seconds. It takes 6 seconds to complete one full cycle. Here in 1 second, how many cycles does it complete? 2 cycles in 1 second. Yes. I'm sorry? That's right, yeah. Yep, so it completes more. The angular frequency or angular velocity is higher, and it completes greater number of revolutions in a certain number of time. Okay. Now, that's your introduction to your sinusoidal and harmonic functions. Now, what will happen if I did this experiment? Okay, so I have so if I were to pull this cart to a certain distance, so imagine that this is a frictionless surface. If I were to pull the spring and let go, what is the cart going to do? It's going to? What do you mean by keep going?
Keep going, non-friction surfaces. It's going to go around.
Yeah, so if I pull it like this and let go, what is the spring force going to do? It's going to push it back.
Oh, it's a spring.
So it's a spring, yeah. So this is going to, it's going to oscillate. So if you were to plot the position, so let's say x of t is the position of this car, and if you wanted to plot this as a function of time, what is this thing going to look like? So let's say you start the experiment, let's say this is x equals 0, okay, and you pull it to this point, okay, and then you let it go. Let's say at this point x equals 2. Okay, and you start your experiment at this point in time. Okay, and if I ask you to describe the motion of this particular carriage as a function of time, how would you describe it? Okay, so it's going to oscillate back and forth, and your expression is going to look something like this. All right, so you want x equals some number a, which represents the amplitude. So you could do the experiment by pulling it up to 2, or you could do the same thing by pulling it up to 4 or 6. The more you pull it, the larger is going to be your amplitude of oscillations. Do you agree with me? So if I pull it up to 2, it's going to go up to 2. Then it's going to go down to -2, +2, -2, +2, etc. There is no friction, so it's not going to die down. All right, so it's going to oscillate between here, from here to +2. Then it's going to go back to -2, 0, +2. All right, so it's going to do this. And you can increase the amplitude and you'll get different curves, but they will all have the same form, if you will. Okay? Now, what would happen if I start the experiment from here, I'm pulling it a certain distance, like I'm going from 0 to 2 and then letting it go. Now, what if I were to start time at this instant? I'll pull it to 2, and that point represents t equals 0. What would x be at t equals 0? So what would the graph start from here? And we call that as a phase shift. Okay? In terms of your two-link or one-link robot, you could start the link here and follow it as it goes around a full circle. Or you could start it right here. So let's say I started at this point here, pi over 8, and then I let it go around a full circle. If I were to plot, so x equals L cosine omega t plus phi, and y equals L sine omega t plus phi. If I were to give this a certain angular frequency omega, and if it had a certain length, this represents the phase shift. If this quantity is 0, then your link is starting from theta equals 0. If this quantity is non-zero, then your link is starting from a non-zero theta. And this represents that phase shift theta. Okay? All right, so we have another 5 minutes more. Let me see if I could rush through this. All right, so there are some homework problems where they change the frequency of oscillations and they ask you to plot that. The MATLAB codes that I've posted should help you with that. And I will tell Peter that I didn't have enough time because he took the test and that you need a little bit extra help, and he'll help you with the homework. I want to cover one more topic before we close, and that is how do you add two sinusoids or harmonic that have the same frequency? Okay, so I have a circuit here, and I want to find the total voltage. It's the sum of two individual voltages that vary like this. Okay, so these represent, if you were to treat this as two separate sinusoids, what would the number 6 represent? The amplitude. And the number 2 represents? So it's of this form, right? X equals a sine omega t plus phi. A represents the amplitude in length, which is meters. Omega is?
Omega is the angular frequency.
Angular frequency. The units would be? Radians per second. Phi would be the phase shift in radians. Okay? So here, 6 is the amplitude, 2 is the frequency, and there's no phase shift. They're both 0. Okay, so if I wanted to add these two sinusoids, so if I wanted to superimpose these two waves that have the same frequency, how do I find out what my resultant wave is? Okay, it's also going to be a sinusoid or a cosine. So it's a harmonic function. So let's say the answer is some magnitude sine omega t plus phi. I have to find out what this m is, I have to find out what this omega is, and I have to find out what this phi is. Okay? And on this side I have 6 sine 2t plus 8 cosine 2t. All right, so what is sine of a plus b? Yeah?
It's sine A plus sine A sine B minus cosine.
Nope.
Oh no, it's sine.
So there are two formulas that you should be familiar with. Sine of a plus b and cosine of a plus b. Who can tell me what these two are?
Sine A sine B minus cosine.
Sine, cosine, sine, cosine. Sine of a plus b is sine of a cosine of b plus cosine of a sine of b. All right? So let's use that and write this. So I would have sine omega t plus phi would be m times sine omega t cosine phi plus cosine omega t sine of phi. And on the right-hand side, I have 6 sine 2t plus 8 cosine 2t. Okay? All right, so I'm going to compare these two sides, and I'm going to... What's up?
You spelled E with the crossover. With the second one, when you came down, you had me with sin A, los, I said los, cos B, plus cos A, sin B. Now when you brought it down, where do you,
So I'm using this expression, sine of A plus B. Sine of A cosine of B.
so WT is just one unit?
WT is A and phi is B. Look at it that way.
Okay. I thought there was like 3 different units.
No. W and T together is 1 unit.
So is it W or is it omega? Or is W
Omega.
I mean, so it's like the little horseshoe thing?
It's like that. It's almost like a W, but you curl the ends and that's omega, like so. Okay? All right. So m sine omega t. If I took m sine omega t, what do I have left? Okay, so m cosine phi is the coefficient for sine omega t, and m sine phi is the coefficient for cosine omega t. And on the right-hand side, I have 6 within parentheses sine 2t plus 8 within parentheses cosine 2t. So look at the left-hand side and the right-hand side. Okay. Now, what can you say about this omega? So these two waves have the same
Time. I mean, not T.
this,
Period.
yeah. So the answer is also going to have the same period. So, or angular frequency. Okay. So now let's compare the left-hand side and the right-hand side. I have sine 2t inside the parentheses, and I have sine 2t inside the parentheses. I have m cosine phi here and 6 here. So that tells me that m cosine phi has to be equal to 6. All right, and the coefficient of cosine 2t is m sine phi, and that has to be equal to 8. Okay? So from this, I could find m. First thing I would do is square and add. All right, so I would get m squared cosine square phi plus sine square phi. Now on the right-hand side, I'm going to get 100, right? 8 squared plus 6 squared. Yep, that's going to become equal to 1. So m squared equals 100, or m equals 10. Just 10, right? M squared is 100, so m equals 10. Okay? And now I need to find phi. So if I'm given these two, I can divide one by the other. So I would say m sine phi divided by m cosine phi equals 8 divided by 6, which implies tangent of phi is 8 divided by 6, or phi equals, as simple as that. So you found out, you've taken two sine waves, or two harmonics, with the same omega, and you have superimposed or added those two waveforms to get one waveform, and here's the final answer. Okay? I think with this much you should be able to do all the homework problems, and anything that you need to plot, I've uploaded some MATLAB codes that should come in handy. So try both of these, and Peter will also help you with your homework. Okay? I'll see you a week from today.